Okay. So, hi everyone. Well, today we have Francesco Benini. He should have been the person giving a talk, a physical talk, when coronavirus started. So this invitation, well, we made the invitation long ago for this talk. So finally the talk will be happening online, as you see, but it's great to have you, Francesco. And yeah, Francesco will be telling us about the superconformal index and gravitational path integral. So stage is yours.
Yes, so thank you very much for the invitation to give this talk. Of course, it would have been much nicer to be there in Paris. But on the other hand, I'm very happy to give this talk because in the second part, I will present some work in progress, hopefully soon to appear. So some work with Ofer Aroni, Ohad Mamroad, who is a student of Ofer, and Paolo Milan, who is a postdoc in Technion. While in the first part of the talk, I will review some older work of mine and Paolo, which is a sort of precursor to the second part. And of course, please interrupt at any time with comments or questions. Please don't write in the chat because I cannot see it because I have full screen. So you should unmute yourself and speak. All right. So, well, as we know, one of the big challenges of modern theoretical physics is to formulate and understand quantum theories of gravity. If we work on flat space, we have a great theory of gravity. This is string theory. We have a perturbative definition of this theory, and we know about some non-perturbative objects in this theory, like D-branes and so on. On the other hand, if you are happy with working in anti-de Sitter space, asymptotic anti-de Sitter space, then we can use ADS-CFT, or the holographic formulation, to actually give a complete and non-perturbative definition of quantum gravity in this space in terms of an ordinary quantum field theory that lives on the boundary. So somehow in asymptotic and de Sitter space, we are in a slightly better footing. Now, if we want to use the holographic description of gravity, maybe or probably we want to study gravity in a regime of parameters in which it resembles in some way gravity in the real world, a sort of phenomenological regime. What do I mean by that? Well, we probably want to discuss gravity in a large ADS space, large compared with the Planck scale, such that the quantum corrections are small. And this in the quantum field theory means that we are dealing with a limit of large central charge, or it's usually called large n. And this is not a problem. This is a limit that we understand, we can deal with. In fact, in many cases, it simplifies the theory. On the other hand, probably we want this space also to be large with respect to the scale of higher derivative corrections to unsteady gravity. This correction comes from integrating out various massive modes. And this, on the field theory side, means that we have to deal with a quantum field theory at strong coupling. And this, on the one hand, is great. But on the other hand, it means, I mean, it could be a problem, it is a problem, if we want to use this quantum field theory to define for us the quantum gravity theory, and if you want to do computation in the quantum field theory to learn about quantum gravity. Because then we have to do computation in a strongly coupled quantum field theory, and this is hard. And so the idea that I will push in this talk, which of course is not a new idea, is that we can try to take advantage of modern non-perturbative methods that have been developed, say, in the last few decades, and that are being developed now, and try to perform computations and strong coupling in the quantum field theory and use them to learn about quantum gravity in ADS. So now, if we have a quantum theory of gravity, we can ask many questions, of course, and the type of question that I will ask in this talk will be about black holes and their entropy. In fact, we know since the work of Bekenstein and Hawking that black holes have an entropy, which is given by the area of the horizon divided by 4g Newton, plus some other dimensional field constants. And the fact that the black hole has an entropy means that really we should think of it as an ensemble of states in quantum gravity. And if you use the holographic description, then this should correspond to some ensemble of states in the boundary quantum field theory. And so this gives us a statistical physics point of view on this story. In particular, we can think of this entropy as the logarithm of the number of microstates in the microcanonical ensemble. And if we do that, then the leading contribution to this number of states will come from a quarter of the horizon area, but then there will be all sorts of corrections, perturbative, non-perturbative, which will come from quantum effects. So this will give rise to the quantum entropy of the black holes. And then this picture, of course, raises very natural questions. First of all, if this is the 0th order step, can we reproduce the Bekenstein-Hawking entropy from a computation in the boundary theory? And then if we can, then can we compute corrections in this boundary theory that would be quantum corrections in gravity? And ideally, can we compute all corrections and resum them and obtain the actual exact integer number of microstates for given charges in a given charge sector? Of course, these are very natural questions that have been asked long ago, in particular in the context of flat space, starting with the seminal work of Strominger and Baffa. They showed in a particular case of BPS black holes in asymptotically flat space that string theory can reproduce the Bekenstein-Hawking entropy of these black holes. And then since then, there's been a huge amount of work and with enough supersymmetry, in fact, corrections can be computed. In some cases, with a lot of supersymmetry, one can actually compute all the corrections, resum them, and obtain this integer number of states. So lots of work has been done, which is really astonishing. On the other hand, given the lack of a non-perturbative definition of string theory, one could wonder or could be worried, one could ask to what extent this program can be pushed with lower supersymmetry, because as we lower supersymmetry, more and more non-perturbative corrections become important, and at some point we might have a problem. And so for me, this is at least one motivation to study black hole entropy in ADS space, where we have a complete and non-perturbative definition of the theory to begin with. Okay, so what about black holes in ADS space? Well, of course, the case of the BTZ black hole in ADS3 has been understood long ago. In fact, we can say that even in the first paper of Strominger and Baffa, they use some duality frame to exhibit some ADS3 in the near horizon and to relate it to a CFT2. The case of ADS spaces in 4 and more dimensions took a little bit more time, but now we understand also in these cases things work. In particular, we have now many examples in which we can look at the boundary quantum field theory at large n, and we can reproduce the Bekenstein-Hawking entropy of black holes in these ADS spaces. And as I said, now, many examples have been looked at. We have various setups, various dimensions. Of course, this is a more recent line of research. So we don't have the same huge amount of work that has been done as in flat space. So people started to look at some corrections, but there is a lot to do.
Sorry, Francesco, when you
Yes.
say it's been reproduced, this is for supersymmetric black holes.
For black holes with a lot of supersymmetry. So I think
How many sources?
I think 16. I think 16. So this will be.
So you mean 16 in ADS? Isn't that too much to have a black hole?
Supercharges. The Gutowski real has 2 supercharges. I don't think any of those has more than 2 supercharges.
No,
Yeah,
but those works are in flat space.
And this is ADS4 years of
So
Sean.
here I was talking about flat space. So you do compactification on, I think it's type 2A on T6.
No, I meant for the ADS black holes. So if you're looking at indices, you need some supersymmetry, I guess.
Yes.
So what's the minimum amount of supersymmetry that you need in order to be able to reproduce the black hole entropy from a QFT computation?
So yeah. So in ADS, these black holes have two supercharges. Well, so far, what has been done is to look at the Bekenstein-Oki entropy. And then, so some correction have been computed. So what people have done so far, in particular, Pando Zeiss and collaborators, is to, so apparently it's very hard in general to compute these corrections. They did some semi-numerical analysis, and they looked at the logarithmic corrections. So you know that there is a log n, or a log of the area, and they tried numerically to reproduce this coefficient. This was done a couple, 2 years ago, 1 year ago. And in ADS4, yes. And I believe that in that context, they were able to match it with a one-loop computation in M theory.
And is there any hope to do non-supersymmetric black holes?
Well, there is always hope. But yeah, so far, and at least in this approach to look at the boundary theory and make a computation there, I think all of the work essentially has been done on supersymmetry. There are, there are a couple of works. Finn Larsen, I think, had a paper in which you try to, of course, you want to go beyond supersymmetry. But sorry, you face a problem that you have to do a computation in strong Campo quantum field theory. So it's hard, but people is moving in that direction.
But the method of localization by construction is based on supersymmetry, isn't it? Right? If you...
Yes. Localization works for supersymmetric theories and supersymmetric observables. As I said, I mean, of course, you're always free to hope that maybe there is some way of adapting it and maybe computing something beyond, but yeah.
What I mean, there's nothing in a sense, because the nice thing about two-dimensional CFTs is that there's this strong coupling Cardy formula, which is doesn't need supersymmetry. There's no analog of that in these higher dimensional setups.
Yeah, so it seems that there is an analog for supersymmetric theories in the sense that it's been, so in the supersymmetric case, you can do the computation. So if you want, you can compute, and this is what I will talk about, the density of states for large charges, for instance, in the Cardy limit, and you can compute the energy of the vacuum, and then you can compare the two, and you can see that there is a Cardy formula at work. But it's not derived from first principles. It's an observation because you can do the computation in the two regimes. And then there is some recent work of Abhijit Gadde, in which he points out some SL3Z structure in the index. But it's not modular invariance. It's more complicated than that. And it's possible that one can use that in the supersymmetric setup to prove from first principle that there can be a Cardy formula. And then if this is the case, then you can ask, okay, is it possible to extend it to non-supersymmetric setup? I don't know. This is all speculation.
Okay, interesting.
Yeah, let's keep going, and maybe we can leave this discussion for later, Peter.
Yeah. Okay, so what I will talk about in this talk will be one of these examples, and will be the example of ADS5. And in particular, I will look at charged and rotating BPS black holes in ADS5, in particular the Butovsky-Real black holes. So why I will talk about this example? Well, first of all, because this example remained as a puzzle for a long time, almost 15 years, since work of Maldacena and collaborators in 2005. And now we understand this case. But also because it seems that in this particular example, we can do quite detailed computations. And so a very detailed analysis might be at reach. And this example seems to be, from the computational point of view, easier than other examples. Okay, so what will be our strategy? So we want to count states in the quantum field theory. And in order to do that, we will employ or compute and construct a grand canonical partition function So this is a sum over all the states in the theory, and the states are weighted by some fugacity. So Q is the charge of the states, Y is a variable, is the fugacity. So this partition function will depend on these fugacities. And then by expanding this function, one can extract the degeneracy of states at a given charge. Now, of course, computing a partition function in a strongly coupled theory, it's very complicated, it's a very difficult problem. So what we will do will be to exploit supersymmetry and use a supersymmetric observable and try to extract the information from there. At the same time, so this definition of a partition function is a Miltonian definition, if you want. This is a sum over states. But there is an equivalent path integral definition of this object. You go to Euclidean time, you compactify time, and then the path integral on this Euclidean manifold computes for you the trace over the Hilbert space. Now, holographically, such a partition function is computed by a Euclidean gravitational path integral, whatever this is, with fixed boundary conditions that corresponds to the boundary theory. And then what you are supposed to do is to integrate over all configurations that have the correct boundary condition, and you have to sum over all of them. In fact, if you want, this is precisely what Witten did when discussing how the Hawking-Page transitions appear in ADS-CFT. You have some boundary conditions, and then you can attach two different geometries, ADS5 and the thermal ADS and the black hole, and then you can discuss, you can reproduce a phase transition. However, in our context, we are looking at a supersymmetric setup, and we have at our disposal localization, and so this will allow us to do a very detailed analysis in the field theory and try to learn something from this detailed analysis in gravity. And what we will find, at least in this specific example, is that, first of all, complex saddles will play an important role. And moreover, that not all complex saddles contribute, and we will provide some criterion for which saddle actually should contribute. Now, the fact that complex saddles play a role should not surprise us. I mean, if you have a real integral in one dimension and you do saddle point, we know that complex saddles in the complex plane could in general contribute to this integral. And we also know that in general, not all complex saddles contribute, and we know how to determine which ones, because one is supposed to do steepest descent and Lefschetz symbols. So we have precise rules to understand that. But of course, once we go from one dimension to a path integral, which is an infinite dimensional integral, things are extremely more complicated. And in general, we are not able to do this analysis. So somehow this discussion should hopefully be an alternative way of understanding this. Okay, so this is essentially the summary of the talk. So if you have other questions, this could be a good time. All right. So the setup that I will discuss is the most basic and most studied example of ADS-CFT. It's tied to B string theory, this 5 × S5, which is dual to 4-dimensional SUN n equal to 4 superunion Mills. In this geometry, in ADS5, BPS black hole solution have been constructed. These are the black holes of Gutowski-Real, then generalized by other authors to more general charges. And these are 5-dimensional black holes in the sense that they can be constructed in 5-dimensional gauge supergravity. They span the S5, so really they are localized in 5 dimensions. These are large black holes. And the questions that we'll try to ask are, so first of all, does n equal to 4 superunion Mills contain the correct number of BPS states to reproduce the black hole entropy, the Bekenstein-Hawking entropy? And then if it does, can we actually try to extract hints of new physics that go beyond Bekenstein-Hawking? Let me just give you some properties, some features of these black holes. I don't want to go into the details. So first of all, these black holes have 2 angular momenta because we are in 5 dimensions. they have 3 electric charges. These are the cartons of SO6, which is the R symmetry of n equals 4 pyramids, is also the isometry of S5. These black holes are both supersymmetric and extremal. They preserve 1 complex supercharge, so it's 2 real supercharges. Since they are supersymmetric, they satisfy the BPS relation, so the mass or energy is a linear function of the charges, but they are also extremal, and because of that, they also satisfy another, the charges have to satisfy another nonlinear relation if we want to have a large and smooth black hole without naked singularities. So at the end of the day, we have a 4-parameter families of black holes. Since these black holes are extremal, in the near horizon, we have ADS2. This S2 is fibered over some S3, and we can compute the area of the horizon, of this S3 horizon, and this gives us the formula for the Beck-Stein-Hawking entropy. So here is the formula, and essentially this is the formula that we would like to reproduce. Notice that, yes.
Just a very naive question. What you're doing is just in 5-dimensional supergravity, right? For
Yes.
now, okay.
Yes, then we will discuss that we can uplift these to 10 dimensions because these are consistent truncation. But for now, we can do everything in 5-dimensional gauge supergravity.
Isn't there some strange structure to the horizon as well? I thought these. I thought these Gutovsky-Real black holes had a rather strange horizon structure. They weren't straight S3. I thought there was some nil manifold involved.
Well, you're surely more expert than me.
No, it's a memory from a decade ago.
So as far as I understand, okay, there is an ADS2, and the only peculiarity, I mean, this is common to the rotating black holes, is that it's not a product, but ADS2 is fibered over S3. But at least if you impose these nonlinear relations, you don't have the closed time like curves.
No, it's not that. It's just a funny topology, and therefore doesn't quite fit the usual picture of a sphere across an ADS with vibration. It's got some other property. Anyway, it's a poor memory probably.
You're maybe right. I mean, the thing I know is that it's actually ADS2 fiber over S3 and not the opposite. Yeah, I don't think I can give you more details. So anyway, this is the formula that we would like to reproduce. And here there should be the cosmological constant. But I'm already using the variables of the field theory description. So here there is I use n, which is the rank of the gauge group. And we want to discuss large and smooth black holes with small curvature. So in this case, all charges, so angular momenta, electric charges, and the entropy should scale like n squared. Okay, so we want to count states in the field theory for given charges. But as we say, this is a hard problem because the theory is strongly coupled. So a good place to start with is a supersymmetric observable, which is the superconformal index. So this object counts with sign, that means bosonic minus fermionic, BPS states on S3. And here is the Hamiltonian definition of the index. So this is a trace over the Hilbert space on S3. There is a -1 to the fermion number. Then there is this term, which is the anti-commutator of the preserved supercharge Q and Kager. Beta is the radius of the circle. And then we can put fugacities for all the charges that commute with the supercharge Q. And it turns out that there are 4 independent combinations. And to each of them, we attach a fugacity that they call PQ, Y1, and Y2. We can also use chemical potentials, tau, sigma, and delta. And essentially, these tau and sigma are related to the angular momenta, J1 and J2, while these Y or delta are related to 2 charges for global symmetries, which are these differences of R symmetries. And something that I have to stress is that since if we want a supersymmetric observable, we can put at most 4 independent fugacities in this object, even though we have 5 charges in the game. But if we put 5 charges, then the object is not protected. Okay, so we have this object. This is protected by supersymmetry, and in fact, there is an exact integral formula for it. The details of the formula are not important. I will not use it. Suffice to say that this is an integral over the maximal torus of the gauge group. And the integrand, well, here there is a prefactor, which is some function. Here there is an integrand, which is given by what is called the elliptic gamma function, some special function. And moreover, it turns out that it is useful to introduce a fifth chemical potential, delta 3. However, this is an auxiliary variable. It's not a new variable because of what I said here. So it's just a function of the other ones. So the number of variables is 4. Okay. So, so what are we supposed to do with this index if we compute it? Well, the index encodes the weighted fugacities in the sense that suppose that there is a single charge and a single fugacity. What we are supposed to do is to Taylor expand this index, and then we look at the term y to the q. So the exponent will be the charge that we are looking at, and then the coefficient in front of it will be the weighted degeneracy of states. So this is degeneracy is the one that we want to extract. It will be supposed to be the exponential of the entropy. And we can extract it with a Fourier transform. And what you obtain is this formula here. And then if you assume large degeneracies, you can apply standard point approximation, and this reduces to a Legendre transform. So we just obtain the standard results in statistical physics that the entropy or the microcanonical, the logarithm of the number of states in the microcanonical ensemble is the Legendre transform of the essentially free energy in the grand canonical ensemble. However, I mean, if we take this perspective, we should be a little bit careful because really we are trying to determine the coefficient of a term in the series, but where the exponent goes to infinity in the larger limit. So somehow we have to run behind this coefficient and follow it as we go to larger and larger powers. Now, there is a natural question that always pop up that I don't have time to go into details unless you ask me at the end, which is the fact that, okay, we are looking at an index, a Witten index, and not the true partition function. So it's bosonic states minus fermionic. Should we worry about large cancellations? Are we computing the degeneracy of states at all? And in fact, it turns out that one can formulate an argument, which goes under the name of I extremization, that tells us that at least at leading order in N, the superconformal index does capture the true degeneracy of states. And this argument is similar to an argument that Sen gave for black holes in flat space when he formulated his entropy function. So I will not go into explaining this. But there is an argument. Okay. So now what we want to do is to do the larger limit of the index. Of course, so a natural approach is to try to apply the direct saddle point approximation to the integral form that I showed you. And in fact, this is the approach that was taken 15 years ago by Maldacena and collaborators. However, it turns out that this is a difficult analysis because there is one saddle point that is easy to find, or at least they found. But this saddle point describes a gas of gravity in ADS. It does not see the black holes. And this was the origin of the puzzle. Supposedly, there are other saddle points in the complex plane, maybe, which describe the black holes, but have not been found so far. So then in the last few years, people have developed other techniques or other approaches. So one is the so-called Tardy limit, in which you take a high temperature limit, which is a limit on the chemical potentials. And this is a limit that captures states with charges much larger than the central charge. And then after you take this limit, you can also take the large N limit. And so this is gonna capture, if you want, black holes whose charges are much larger than N squared. On the other hand, you can try to compute just the larger limit without any limit on the fugacities. And this is what I'm going to talk about, and it's based on a different formulation of the index. This is what I will talk about. And then let me just mention some other approaches that have been developed more recently. One is to set the point approximation, but for some non-analytic extension of the index of the matrix model. And another one is to try to approximate the index with the Gross-Witten-Wadia model with complex couplings, and then try to compute some corrections. But I will not talk about this. I will only talk about this beta ansatz formulation. Okay, so what is this? So essentially, this is just an alternative exact formula for the index that you can obtain, if you wish, by some manipulation of the integral formula. And let me just discuss the case that the two angular chemical potentials are equal, because then the algebraic treatment is easier. In fact, everything can be generalized to the case in which they are not equal, but everything is more cumbersome. So here is the formula for the index. So let me explain. So first of all, there is no integral in this formula, but there is a sum, and there is a sum over the solutions to a set of equations that we call beta ansatz equations. And these are equations for essentially complexified holonomies. So they are as many as the rank of the gauge group, and they live on a complex torus, whose modular parameter is the chemical potential for for the angular momentum. So these equations look like Qi equal to 1. There are as many equations as the rank of the gauge group, and these Qi are some beta ansatz operators. So I will write better this equation in the next slide, but essentially they look like the beta ansatz equation for some elliptic integrable system. So you're supposed to solve these equations, and then once you have solved these equations, you have to plug in the solution into these functions. And this prefactor is the same as in the integral formula, so I'm not going to write it again. This z is the integrand of the integral formula, and this h is a Jacobian of these beta ansatz operators.
Okay. Sorry, if I may ask, this also come from localization? You get that from some equivariant localization or something like that, or what is it?
You could, but more simply, you take the integral formula, which can be derived either from localization or from the fact that the index does not depend on the gauge coupling. So you can compute it as weak coupling, and then it's the same as strong coupling. So anyway, is that you take that formula and then you just manipulate, because this formula is a contour integral. You integrate over circles, and then you have to resum the rest. You do it in some clever way, and if you do that, you obtain this formula. So it's just a manipulation, if you wish. There is also a more physical and interesting interpretation of this, like a reduction on a torus and going down to a two-dimensional topological field theory, but I'm not going to discuss this. Any other question? Okay. So in fact, this is the form explicitly of the beta ansatz equation for n equal 4 superior meals. And okay, if you are familiar with the integrable system, these look like beta ansatz equation for an elliptic integrable system, because this theta 0 is essentially a Jacobi theta function. And so these equations, in fact, are defined on the torus, and are invariant on the RSL2Z, and so on. So in fact, in this formula, solving this equation is the hardest step, because once you have solved these equations and you have your solution, you just have to plug them into the function, and that is easy. However, luckily, it turns out that we know not of all solutions, but we know of a class of exact solutions at finite n.
Sorry, Francesco.
Yes.
Was there some associated physical system who had integrable physical system, or some auxiliary integrable physical system?
So I cannot answer precisely, in the sense that, so what you can do, So you take your index, which ultimately is a partition function on S1 times S3, and you do a reduction on a torus. So one is the circle, the other is the op fiber, and you go to 2 dimensions. And you do it in such a way that you get a 2,2 theory in 2 dimensions, which is a topological A-twist. And now the idea...
sorry, and this theory lives on part of the tree-sphere?
Yes, on the base of the op fibration.
I see.
And then the idea is that now you have a 2-dimensional 2,2 theory, and you can apply the Nekrasov-Shatashvili story. And so, for instance, the vacua of this theory should be related to an integrable system, and then the partition function will be related to something in the integrable system, and so on. The fact is that, as far as I know, all explicit examples, or maybe almost all explicit examples, for which we know the Hamiltonian of the integrable system, are 2,2 star. So you start for 4,4, and then you break supersymmetry in some canonical way. If you take a generic 2,2 theory, I think that the corresponding integrable system is non-unitary. And again, I'm not an expert, but I don't know of exact examples in which exactly a definition of this integrable system and everything follows. So I don't have an answer if you ask what is the elliptic integrable system in this case, but maybe the expert can give a better answer.
Okay, thanks.
Okay.
Can I also ask something? You hear me?
Yes.
So if I understand here, you are not looking for a saddle point. You are solving exactly these equations.
Yes, yes. So, I mean, you could try to solve this equation in the large N, but it turns out, and this is something special to this example, that you can solve these equations exactly. But anyway, so on the face of it, the solutions to these equations have nothing to do with saddle points of the original integral formula, because it's just we have manipulated it in some way. We have some the residues. These solutions somehow should represent some residues. So in principle, there is no relation. But as we will see, in fact, there is a close relation, which I don't have a physical explanation for, but it will be an observation at the end.
But okay, but you have complexified the modular parameter, right? It was real to begin with.
Well, no, I mean, in the Hamiltonian definition is complex. I mean, you're summing states with some fugacities. So if you want the integral definition as a partition function, then okay, then maybe you want to restrict to some real values. But if you use the Hamiltonian definition, no.
Okay. Right, thanks.
And so far we can work with the Hamiltonian definition. Okay. So, okay, so we have these exact solutions, and these solutions are labeled by 3 numbers that are written here. So the product of the first 2, M and N, is equal to the rank of the gauge group, and then R goes from 0 to N. So what are these solutions? Well, the solution is very simple. Essentially, you take the torus, and these complex eigenvalues, these complexified holonomies, organize into a line on the torus. So for instance, a solution that I will call the basic solution, all the eigenvalues are along the B cycle of the torus. And then you can use the cell to Z to generate other solutions. So for instance, there are what I will call T-transform solution, in which as you go once around the B cycle, you also go some number of times along the A cycle. So you rub these times, well, in this way the torus. And more generally, you have all the SL to Z transform solutions. And then it turns out that there are also more general subgroups when this M is bigger than 1, in which the same cycle is rubbed multiple times along parallel lines. Okay, and the full classification of this class of solution is given by these 3 numbers. So we will study these solutions and the contribution of these solutions. Now, let me mention that has been conjectured the existence of also some continuous family of solutions, but I will have nothing to say about those, so I will just disregard those. Okay, so what we have to do is simple. We have to take these solutions one by one, plug them into the functions, and take the larger limit. And it turns out that the larger limit is a discontinuous analytic function of the fugacities. And this is common. This is sometimes called the stock phenomenon. At any finite n, the index is an analytic function of the fugacities. In particular, it's continuous. But when you take the larger limit, you can have multiple exponentially large contribution, which are summed. And in some region of a parameter space, one exponential dominates, and you have some analytic function. In some other region is another exponential that dominates, and you have a different analytic function. And then when you move from one region to the other one, you essentially have a phase transition, right? This is just the physics of phase transitions. And in order to represent these discontinuities, it turns out that it's useful to define this function, square bracket. How is this function defined? But this is very simple. It's essentially a function that in some sense takes the fractional part of the real part. So you use tau here to construct this strip of width 1. And then you take delta and you have to shift it by integers until the real part, well, you shift the real part by integers until it goes inside the strip. So it's sort of slanted version of taking the fractional part of the real part somehow. So anyway, you plug these solutions, and in particular for now, let me look at the basic solution, just the basic solution. So this essentially this solution here. And you plug into the function, you take the larger limit, and you discover that there are two regions in parameter space. I will call them first case and second case. In fact, they are very similar, so I will only discuss first case in this talk, but remember there is always also a second case. And the larger limit takes a very simple function, form, which is written here. And we need this square bracket to write the result. Okay, so now we have this very simple expression. So what we have to do, we have we try to extract the entropy from it. So let me call this bracket x such that the expression is simpler. So here it is. You remember that x3 is really a function of the other ones because there is a constraint. And so now we have to do a Legendre transform if we want a constrained Legendre transform of this. And luckily enough, when we do that, we exactly obtain the formula for the entropy of the black holes. So this is the formula that I wrote at the beginning for the area of the horizon, essentially. And here it is specialized to the case tau equal to sigma, but in fact, everything can be generalized to tau different from sigma. It's just more cumbersome, but we did that with Alberto Zaffaroni and some students. And for instance, in this formula, instead of tau squared, you get tau times sigma. In this formula, instead of 2 tau, you have tau plus sigma, and so on. And here you have the two angular momenta. But okay, so this is nice, so it works. Just this particular contribution to the Bethe-Ansatz formula at large n reproduces the black hole entropy. Is there any question so far?
Excuse me?
Yes.
I don't understand. You didn't take into account all states, only very specific, and nevertheless you reproduced the entropy.
Well, we are looking at a supersymmetric problem. So the black holes are BPS, so they have 0 temperature. And in the field theory, we are looking at supersymmetric states. So they are, so yes, so essentially they are the states at 0 temperature.
But the Bethe-Ansatz equations contain more solutions than you use, yes?
Yes. So yes. So if you want, is the surprising part that in the formula. So let me go back to the formula. So you are supposed to sum over all these solutions to these equations. Yes. And so far, we only taken one solution. If you wish, we have been lucky. And these solutions reproduces the leading in n contribution, or at least the contribution to give you the black hole entropy at leading order in n. Yeah. And then you can ask what.
I feel puzzled.
Well, I mean, yes, I mean, of course, we should ask what about all the other contributions? What they do represent. Let me stress also that when we took this large limit, well, here I'm writing equality, but there are all the, I mean, it's not an equality. I mean, there are all the corrections. This is the order n squared contribution, and then there will be 1 over n corrections, there will be logarithmic correction, there will be exponentially small corrections. So even for the basic solutions, there will be all the corrections.
No,
On top of that, there are also the other solutions.
I'm ready to accept the large limit, but even in the large limit, I suppose there are more solutions of these beta equations than you used.
Yes, yes, there are all these other solutions that I described here, and many more, and maybe more, these continuous families. So I'm not, I will not discuss these continuous families, but now I'm going to discuss the other ones. So of course, you are perfectly right to ask this question. What about the other ones? And this is what I'm going to discuss next. Okay, so what is the role of all the other beta ansatz solutions? Yes, so I will try to be quick because I'm a little bit behind, but I hope I will convey the main idea. So in order to answer this question, so let's try to think about what we are computing. So far, I put the emphasis on a counting problem. No? We have been counting states. But as I said at the beginning, we can think of the same problem from the path integral point of view as computing a partition function, some Euclidean partition function on S3 times S1. And these objects are the same, the suitable regularization, because the index starts with 1. There is a single vacuum on S3, or if you want, there is a single identity operator. And here, depending on the regularization, you can have a Casimir energy. I'm choosing a regularization in which a Casimir energy is 0. So now, holographically, how is this partition function computed? Well, essentially, you fix the boundary conditions, and then, well, you're supposed to compute a string theory path integral, whatever this is, in which the boundary conditions are fixed, and then you integrate over all string theory configurations with the correct boundary conditions, which semi-classically is approximated by classical saddles, so solutions of the classical supergravity equations of motion, plus corrections. So we are supposed to fix the boundary data and then look for all bulk geometries that can be glued that have the correct boundary conditions. And what are the boundary conditions? Where we have the metric, which is S3 times S1. There is a sort of twisting of the S3 as we go around S1, because this encodes the angular chemical potentials. And then there are holonomies along the S1 or flat connections. This represents the electric chemical potentials. And of course, these gauge fields become dynamic. They are external background gauge fields in the field theory because they are associated to global symmetries, but they become dynamical in the bar. So this, of course, as I say, this is a story that you understand. Witten in his thermal phase transitions, the fairy tale story, the Maloney-Witten story in pure gravity in 3 dimensions. However, here there is a catch somehow, which is the following: that so we are looking at supersymmetric observable in the boundary, and then we know that only supersymmetric configurations contribute to this observable. This is a standard localization argument, because if we have supersymmetric boundary condition and we look at configuration that breaks supersymmetry, then there is a fermionic 0 mode, and then when you integrate over the fermionic 0 mode, you get 0. So once again, this is the standard localization argument. You should look only at supersymmetric configurations, and then of course on top of that, you're supposed to look at fluctuations of all the fields, but only supersymmetric configuration should contribute. So now it seems clear what we have to do. Okay, we take the Lorentzian BPS black hole. In fact, we just reproduce its entropy, and then we go to Euclidean, and then we glue it to the boundary conditions. However, the Lorentzian BPS black hole has 0 temperature because it's extremal. And when you go to Euclidean, the radius of the cycle is infinite. So it doesn't match these boundary conditions because here in field theory, we have a finite size cycle. And in fact, it turns out that there are no real configurations which are supersymmetric and that match these boundary conditions. And so this forces us to look for complex Euclidean supersymmetric solutions.
Sorry, Francesco.
Yes.
Wasn't it to be expected that if you take any rotating black hole, like Kerr black hole, and you try to do its Euclidean continuation, you're going to get a complex solution simply due to the angular momentum?
Well, not immediately, because, well, at least in, okay, I don't know about the general case, but at least for these supersymmetric black holes, you go to Euclidean time, and then, okay, there is a parameter that controls the angular momentum. If you take this parameter imaginary, then the metric becomes real. So you don't just rotate time. There is another parameter you have to rotate, but if you do it, you get a real metric.
I see.
And is the metric which
But there is no one-to-one correspondence, right? It's like all class of Kerr black hole have to do with all class of Euclidean solution, but you don't have a correspondence between one black hole and one Euclidean solution.
So what I'm saying is that if you rotate time to imaginary time, but then there is also the parameter controls angular momentum. If you make that parameter imaginary, then you can get a real metric.
Yeah. But I could also be happy to work with complex metrics. I mean, here you.
Okay.
Okay.
I will be happy to do that. In fact, this will be.
But I understand a bit less is the matching to the boundary condition, because if I'm happy to allow you to work with complex metrics, then yes. Do you still have a problem matching with the boundary conditions with the S1?
No, the point is that if you want to match with the S1, you need non-extremal solutions, because extremal solutions have a radius which is infinite.
And that's independent of the metric being real or complex, is that right?
Well, but it turns out that this is the statement. If you look at supersymmetric solutions with a finite size circle, they are necessarily complex. There are no real and supersymmetric metrics which also have a finite size circle. If you ask these three cases, these three things, reality of the metric, finite size of the circle, and supersymmetry, there are no solutions.
I see. So if I just take the Lorentzian solution, which yes. I guess does have a finite. No. This is non-compact, of course. Yeah. Okay.
In that sense, we need solutions which are supersymmetric but not extremal, which you cannot do with real metrics. So yeah. Okay.
By not extremal, you mean that
the temperature is not zero, so that's why. I mean, the size of the cycle is the temperature, so the temperature is not zero.
Okay. Thanks.
So this might sound like a daunting task, maybe at least to the non-expert. So to me, it seems very difficult at the beginning, but in fact, we can use a trick, a clever trick by Martelli et al., which is the following. So, okay, you can look at the black hole solutions that have been constructed in the literature in ADS5, and there is a 6-parameter family of these solutions because there are 2 angular momenta, 3 electric charges, and the mass. And this family of solution depends on parameters that control these charges. And now if you plug in generic complex value for the parameters, you get complex metrics and gauge fields. So you can get solutions of the equation of motion which have complex metric and complex gauge fields. And now that you are in this complex world, you can impose supersymmetry but not extremality. In other words, supersymmetry and extremality are 2 conditions which are completely independent if you look at complex metrics.
Sorry, Francesco, just trying to understand this better. So if I just take the Kerr black hole, yes. the extremality condition is something like J equals m squared. Then when I go to Euclidean, as you say, indeed, I can make the Euclidean metric back real by turning J to be complex. But then obviously I'm going to be violating the extremality condition, because now I have ij, which is something like ij equals n squared. So is it just this?
No, but I mean,
or it's more complicated?
So if you define extremality as the fact that you have an extremal horizon, in the sense you have a double zero and you don't have a smooth horizon, then, I mean, when you do the analytic continuation, it remains, I mean, you have an infinitely long throat instead of having a capped geometry. Now, what is the consequences on the charges? Okay, I'm not sure. You have to see it, but so I will define supersymmetry. I mean, it's not me, it's in this paper of Martel et al. But okay, we define supersymmetry as the fact that there is a killing spinor, and we define extremality as the fact that there is no, if you want, there is a double zero, and so there is an infinite throat at the horizon, and then the circle is infinite length. And then you have to see what is the consequences on the charges.
Are the charges becoming complex, or they're staying real and you're just changing some other fields to make them complex?
Well, here I'm taking everything complex. So once the metric is complex and the gauge field is complex, the charges are complex, chemical, everything becomes complex.
I see. So the point is, I mean, there's something which we did a while ago with Nick Warner and Clément Rueff about imaginary brains. So you can actually put brains which have imaginary charge in some black hole backgrounds, even Schwarzschild. Okay. And you can actually have those brains have no feel zero force. So if you put some imaginary charge brains in even in Schwarzschild, you can actually make these brains to have no force. So you can argue that the killing spinors of these imaginary brains are actually preserved by Schwarzschild. So I think you can make this, you can apply these techniques even to black holes in flat space. We couldn't get too much mileage out of that, but
okay, yeah, it sounds.
I think that, you know, I mean, what I'm confused about is like, okay, in ADS you use this method and so on, but you know, if I'm to use this method in flat space and, you know, to use these killing spinors, you know, why don't I use it for Schwarzschild or, you know, for some other?
Yeah, I don't know. I'm just saying that here, I mean, if I'm considering these complex metrics and I will impose supersymmetry, but not extremality. And so far I'm doing Euclidean physics. So as you will see, I'm just trying to find saddle points of the putative gravitational path integral.
Francesco, something that I'm confused about now is, at the end of the day, when is this a computational trick? Or are you saying that we have to extend the field space to this larger field space?
Yeah, I'm saying that you have to do it. I mean, I'm saying that this is, yeah, sorry, let me rephrase. I'm saying that when you apply saddle point approximation, you have to include complex saddles, even though your original integration contour was on the real line. And we know this from one-dimensional standard integrals. Right. So if you want, our gravitational path integral, whatever it is on a real contour. These are the fields that we want to integrate over. But once we apply saddle point approximation, if we want to reliably do it, we need to include complex saddles.
Yeah, I understand. Thanks.
Yeah. Okay. So, okay, here I just wanted to show one example, but okay, you got the idea. So I don't want to go into the details. Let me just mention that when you impose this supersymmetry condition, you get some square root, and so there are two branches of the solution, and in fact, ultimately, these two branches will be matched to the fact that in the field theory there were these two cases in parameter space. But I put it there and will not come back to it. So what's the idea? So now we have these boundary conditions. So let me just try to focus on the ideas. We have these boundary conditions. We have all these complex solutions, which are supersymmetric, but not extremal. And we have to find the ones that match with the correct boundary conditions. And so first of all, let's look at the metric. So the boundary metric for all these solutions is S1 times S3 with some twist of S3 as we go around S1. This is encoded by the angular velocities, which by a change of variables is related to the angular chemical potentials. And since the angular variable phi and psi, so these are coordinates on the S3, are defined modulo 2 pi, it turns out that if you shift the angular velocities by integer times some factor, you get the same boundary metric. So this is not surprising. We know that the chemical potentials are defined modulo integers. So here we see that if we shift these chemical potentials by integers, you get the same boundary conditions. However, the solution in the bulk is completely different, because this omega controls the full solution in the bulk, which is somehow smooth. So we have to sum over all these shifts. And there is the same thing for the boundary gauge fields. Also in this case, the holonomy is the gauge invariant. So you can shift the electrostatic potential, which is related to this electric chemical potential, by integers, and you get the same boundary conditions. So the upshot is that you have to, so the boundary conditions only fix this complex chemical potential up to integer shifts. And so you're supposed to sum over all of them. And so now you go to, so first of all, okay, there is some change of variables that you have to do to match with the index. So from omega and phi, you have to go to this tau and sigma and delta. But now you compare with the Bethe-Ansatz formula. So if you look at the Bethe-Ansatz formula, you take this generic solution, you compute the Largen limit, and this is the result that you get. So there are all these corrections, but the leading contribution is this, okay? And essentially, you have this shift of R into tau. This tau check is the same thing as in the denominator. And yes. In gravity, you can compute the on-shell action. So let's compute the on-shell action, and here is the result. And as you see, it's very similar. So there are the 3 chemical potential in the numerator. There are the 2 angular chemical potential in the denominator that I'm taking equal here because I'm taking tau to sigma. So it looks very similar with all the coefficient and everything, but there are a big difference that in the field theory, we only, so, okay, first of all, there is this M does not appear here. So if we want to have a match, we have to set M equal to 1. So let's set M equal to 1. So then there is a match of the coefficient. But now in this formula, there is only a sum over R. So you only shift the angular chemical potentials, and also you shift them by the same amount. While in gravity, it looks like you have to shift all the electric chemical potentials, and also the angular chemical potential, you have to shift them in an independent way. And in the field theory, there's no shift of the electric chemical potentials, or better, this bracket is taking for you a very specific shift, which is dictated by this bracket, but you don't sum. So the upshot is that it looks like there is a match with the T-transform solutions, but in gravity, there are too many solutions. Okay, so we need to get rid of some of them. And how do we do that? So the solution of this puzzle, so let me just take a couple of minutes if I can.
You have 10 more minutes.
Oh, okay. More than enough. So the solution of this puzzle is related to looking at non-perturbative corrections from Euclidean supersymmetric D3 branes. So maybe this is very similar to what Josif was talking about, or maybe not. But, so this is the thing. So first of all, okay, we uplift the geometry to 10 dimensions. This is standard. So now we have S1 times S3, and then we have the S5. And then we look for Euclidean supersymmetric D3 branes, and it turns out that there are these supersymmetric branes sitting at the horizon. So these branes wrap an S1 in S3, and in fact there are 2 possibilities related to the 2 angular momenta. They wrap an S3 in S5, and there are 3 possibilities related to the 3 electric charges. So in some sense, these are similar somehow to giant gravitons, to a Euclidean version of giant gravitons, but in the black hole background. And then you can compute the on-shell action for these branes. And the result is very simple. Okay, so these are the on-shell action, and these branes are going to compute for us non-perturbative corrections to these large n leading in an order m squared result. In particular, notice that all these branes are mutually supersymmetric. So in principle, you are supposed to sum overall possible positive linear combination of these branes. So there is an infinite number of these corrections that you have to consider and sum up. So what is the effect of this correction? So let's see. So, okay, this is the leading contribution where you don't have the branes. And then to the gravitational path integral. And then you have to sum over all the ways of introducing the 3 branes. And then if you bring these to the numerator, this is the expression that you get. So you see that the effect of the branes appears as an order e to the minus n correction to the classical action, to the order n squared term. However, we are dealing with a complexified setup. So this correction could be exponentially small or exponentially large. In particular, if you look at here, you see that depending on the sign of the imaginary part of this action, it could be exponentially small or exponentially large. But if you have some correction which are exponentially large, this really means that as you sum up this correction, you get something which becomes very large, and at some point become as large as the leading contribution. So really what you are describing is some D3 brane condensation that leads you towards some other saddle point. So this means that this saddle point that you're looking at is not really contributing to your path integral. At least this correction makes it completely nonsense. So the criterion that we propose is that only the complex configurations for which all D3 brane embeddings lead to an action with positive imaginary part. So only those should be retained, and the other ones should be discarded. And what we expect is that these signals, this phenomenon that we understand in the context of one-dimensional integral, for which, okay, you can look for complex saddles of a one-dimensional integral, but then not all of them contribute. And you're supposed to do Lefschetz steam balls, and you're going to discover that some of them contribute and some of them do not contribute. And in the lack of the same kind of argument in the infinite dimensional context, we hope that somehow this criterion capture the same types of physics. Okay, so are there questions on this, which is the main idea? Okay, so
sorry, yeah, it took me a while to unmute myself. So when you say that this D3 brane condensation will move you to other saddle points, are you saying that somehow you're going to get new saddle points that you haven't discovered by your analysis, which come about by integrating in this infinite contribution from D3 branes, or?
Well, okay, so from the mathematical point of view, what I have in mind is that probably if I was doing Lefschetz steam balls for this path integral, I would discover that these saddles just do not contribute. And they cannot contribute because physically I have completely distant on corrections, but if I try to resum them, they are exponentially large. A physical picture that I have in mind, but this is kind of vague because we are in the Euclidean context now, is that if I sum up, so I have the leading order n squared contribution, but then you have to sum this other exponentially large contribution. When I do that, they lead to something which is order n squared far away. So probably what I'm going to discuss is another saddle point, which has a different field theory configuration, and if I expand around that, the instant correction are exponentially small. In a sense, I'm doing a wrong expansion around the point where I'm outside of the radius of convergence somehow.
I see. Okay, thanks.
But again, I don't have a very precise understanding of this.
I want to get a sense of what the rules are. So basically you say, I've got an S3 at infinity and I've got time, and I want to fill in the radial coordinate with whatever configuration of branes that look like essentially the original D3s of the ADS5 plus some other D3s that turn up at the horizon. Is that correct?
Yes. So the basic configuration is just gravity without any brane. So I just have gravity with some smooth configuration.
Right.
But then on top of that, I can also place some Euclidean D3 branes inside the geometry.
Yeah, okay. The reason why I'm asking is this sounds like a problem that we ask all the time in microstate geometries. We set up some boundary conditions that look like a black hole infinity and then ask what we can fill it in with. And if you take the D1, D5 system and T-dualize twice, you get a D3, you get a tilted intersecting D3 branes. And so you get your three charges from the three different ways of tilting D3 branes or microstate geometries. And I'm sure there are complexified microstate geometries in exactly the same way. So the question I'm really asking is, if you pose it in terms of filling in boundary conditions that are S3 times Euclidean time with stuff that looks like a black hole, that's exactly the question we ask ourselves in microstate geometries. Okay. And in particular, tilted D3 branes is just one duality frame that describes many of the solutions we have. Okay. So are your instantons just microstate geometries Euclideanized?
Well, I mean, for sure, if you have these microstate geometries which are smooth, but have the same boundary condition, you should include them in the Euclidean gravitational path integral. Now, okay, I don't know if they exist in the context of ADS. I don't know if you have studied those in asymptotically ADS.
No, but that was the way you posed it. You said asymptotically.
Yeah, my problem, yes. So if they exist.
Well, it's S3. So the question is, how do you tell that you're making it asymptotically ADS? Do you put further boundary conditions on your configuration? How does it know it's not in flat space?
Well, because the theory has a gravitational cosmological constant. So, I mean, when you solve at infinity, you're not going to get asymptotically flat.
Okay.
Okay, so the upshot, I'm out of time, is that we have to apply this criterion. Well, we apply this criterion. This is what we propose, and when you do that, this big sum of stuff that you had over all the possible shift collapses to precisely the shift that you have in the beta ansatz formula. So if you go back here, so you go back here, just restricted to m equal to 1. You only sum over this R. So you only shift this angular chemical potential. So if you apply this criterion, you get exact match between what you sum over in gravity and these T-transform solutions. And in fact, you can go on and also compute in the field theory what is the exponent of the non-perturbative corrections, this order e to the minus n, if you want in this formula. We can evaluate this, just the exponent, not the full prefactor, and it also matches with the action of on-shell action of these branes. So the final question, I will spend 30 seconds on this.
Okay, Francesco, yeah, please.
Is what happens for the other solutions m bigger than 1, and it turns out that those are orbifolds. So once you go to 10 dimensions, so you do the uplift, you discover that there are some orbifolds of these solutions that you can do, and they describe all the other, these are some other solutions, and they match with all the other beta ansatz, the contribution to the beta ansatz formula. It's interesting because these orbifolds would be singular in 5 dimensions. So if you study 5-dimensional gauge supergravity, you would not include those. Those look like singular orbifolds or singular geometries, but once you uplift to 10 dimensions, they are smooth. And so you must include them, and everything works nicely. Okay, so let me conclude. So just to summarize, what we did was this careful analysis of the superconformal index using this alternative beta ansatz formulation. And at large n, we found many contributions, which are these beta ansatz solutions. And there is one which reproduces the Bekenstein-Hawking entropy of VPS black holes. All the other ones give corrections that match with complex gravitational saddles that should contribute to the gravitational path integral. And we propose a criterion for which complex saddle should be discarded from this saddle point approximation. And if we do that, we have a precise match with this beta ansatz formula. And then there are some open questions, so maybe I will leave those on the slide if you want to ask, but I will stop here. So thank you for your attention.
Thank you very much, Francesco, for the very nice talk. So what you're saying is basically that as soon as you say this imaginary part needs to be, was it negative or positive, then you match exactly well, you get rid of the amount of saddle points that you wanted, right?
Yes.
Exact. I find it, it's very nice, but yeah.
And let me also, okay, since you asked, comment on this. So in the field theory formula, okay, you take this contribution and you compute the large N. And when you do that, okay, you try to do it in a way that makes sense. So when you take this large N, you find a leading order N square contribution, and all the other contributions are smaller. In particular, you can compute exponentially small corrections. And these are exponentially small, if you want, by definition. I mean, you did the computation in the correct way. Suppose if you did the computation in the correct way, this will be exponentially small. And you get this answer. Mm-hmm. And then the nice thing is that this matches with the on-shell action of D3 branes only if the criterion is satisfied. So for those complex saddles in gravity for which the criterion is satisfied, you precisely get the same exponentially small corrections. While in the other ones that we exclude, you have these exponentially large corrections that from the field theory point of view would not make sense. It will tell you, look, you're just doing your limit in the wrong way because you compute something, a contribution, but what you are forgetting is much larger. Okay, so this is, let me just.
Nice. Well, more questions for Francesco. We had plenty of them during the talk, but please go ahead.
Can I ask a question?
Hi, yes.
Hi, Francesco. So you basically opted for selecting some of the saddle points in the gravitational calculation to match with the field theory calculation. But how do you know, and this was in a sense a point also made by Volodya, that you are not missing saddle points or solutions in the beta ansatz calculations that should be added there?
Yeah, so this I don't know. So as I said, these equations are difficult to solve. For sure, for me, I'm not an expert, so maybe for the expert it's easier. So I don't have the full list of solutions. I gave you some solutions. There are many, but there are some. And I already told you that probably we are missing these continuous families. At small n, we can prove analytically that there are other solutions. And probably this solution exists at large n, and you can ask what is their contribution. So what I can say is that probably this other solution exists, and they will probably give some other contribution at large n that probably have some interpretation in the gravitational path integral. So I'm not claiming that I have found all possible geometries with the given boundary conditions. For instance, you could ask, what about multi-center black holes? Essentially, what I discussed are only single-center black holes that exist in the literature. But what about multi-center black holes? They have not been constructed in ADS, as far as I know, but there is no theorem that says they do not exist. So if they exist, they would probably would have some analog in the Euclidean signature.
I think there are theorems.
Yeah.
So the
they do?
Yeah. So the point is in ADS4. If you work in ADS4, that would be multi-center, but the 5D uplift would be actually a 5D black ring. Multi-center solution exists in 4 dimensions, but the uplift in 5 to either black holes or to black rings. And in the particular gauge supergravity where the Grotowski-Real black hole exists, I think Harvey Real and some other people proved the theorem that black rings don't exist.
Okay.
That's BPS black rings, of course.
Yes,
Non-BPS,
yes.
you can make them. Now,
but still, there could be multi-center in 5 dimensions.
Those I've never. Those are not known even in 4. There are no. I mean, even in flat supergravity, they don't exist. It cannot be 5-dimensional. In 5-dimensional, asymptotically 5-dimensional, 4,1. You cannot build multi-center solutions.
You don't have black Saturns and stuff like that.
No, but they're not. They're not black holes.
They're not
black holes. They're a black ring and a black hole.
So another way of saying what Joseph says is, suppose if there are multi-centers, then you can make a 2-centered guy, and you could load one center up with a certain amount of charge, another center up with another amount of charge, and that would then become a supersymmetric black ring if you did it right. So there has to be an abstraction to multi-centers.
5D you cannot do.
It may not be a complete abstraction, but you cannot, according to Harvey's theorem, there are no supersymmetric black rings, and that really tells you something about a particular two-centered solution that gives you the.
So you can have two centers that rotate one around each other,
but there's no supersymmetric.
Yes. So
supersymmetry, you can make the pig fly. Sure, we can put black rings. You can put everything you want.
It's extreme. There's a simple argument. If you take the cosmological constant to be extremely small, it's basically flat space, and you can make all the bubble geometries and multi-center geometries. You can make them all. But the point is, the minute you turn on the cosmological constant, the supersymmetry of the multi-centered bubble solutions hates the supersymmetry of the ADS, and so they get lifted. And that's what I'm sure happens. That's not been proven, but that's how I understand Harvey's theorem. Multi-centered and ADS don't like each other.
I see.
But you have worse than multi-center, right? Because you will have bubbles in 5D and things like that, which you cannot distinguish from the black hole. So you have some kind of air of topology that can grow everywhere. And
absolutely, but they won't be supersymmetric, I don't think, in ADS.
The bubbles?
Yeah, I don't think so. In ADS4 and ADS5, I don't think so, but that's how I fit Harvey's no supersymmetric black ring theorem into the universe of microstate geometries. I think if you have asymptotic the ADS4 and ADS5, there's some serious problem with multi-centering and the cosmological constant. It's only if you want supersymmetric. They will exist as a non-supersymmetric guy. I'm certain of that.
Now, maybe this is one option. The other option is that, maybe they exist, but, we just haven't been able to construct them, and, don't think anybody has.
For me, it's more a technical issue. It's very hard to build. They're probably not integrable, and I mean, in the sense of integrable system algebraic solution, and it's very hard to find any. And if you apply the one you know, you don't manage. But
yeah, I think in the minimal theory where Harvey has the proof that black rings don't exist, I think there you can make an argument. You can probably take his theorem and use some type of Gibbons-Warner arguments to make some noise against bubbling solutions. But I don't know.
But still, I mean, I don't think that you exclude any other possible solution.
No, I don't.
I mean, we believe in fuzzballs. We want to build them. Of course not.
but it's possible that fuzzballs exist only as things whose energies are lifted by the scale of the cosmological constant. That's a possibility. I prefer that there were supersymmetric ones, but it's. We thought, Joseph and I have discussed this a lot, but multi-centered, there is an issue. And like all no-go theorems, you need to look at the assumptions, because I'm sure some extremely clever person is going to come along and drive a coach and horses all right the way through Harvey's theorem because he made some assumption that wasn't so perhaps explicit. So there could be some clever trick, which you dodge that bullet. But the bullet's interesting. I mean, you have to look at Harvey's theorem and go, okay, how do I get around that?
But Francesco, I wanted to ask you actually about this uniqueness theorem. So when you say compute correction more precisely, which would be toward going to the exact entropy of the black hole, how can you in fact distinguish what is actually counting state of the black hole from whatever would be more like ADS hair or something?
Yes, so this is one of the difference between, if you want, the ADS case and the flat space case, in the sense that in the story of black holes in flat space, what people try to do is to go to the near horizon and really just count the number of states of the single center black hole. In fact, there is a long story that is related to these mock modular forms in which you want to disentangle somehow single center states from multi-center states, and then you use this mock modularity and so on. Now, in the ADS context, at least what I've presented, I look at the full gravity in ADS, and the boundary, the quantum field theory that I use describe everything that happens in ADS. So this is going to capture both the states of the black hole, if you want the single center black hole, but also gas of gravitons or other type of hair outside of it. And if there were multi-center black holes, also those. So for sure, if you want to isolate the contribution of just the single center black hole, you have to find a way to do that. Or more generally, you might be happy to describe all the possible states that include hair and gas of gravitons outside the black hole.
But this is the main issue, right? Because with mock modularity, as you were talking, the tool that you use in flat space is that the single center black hole are the ones that exist for all moduli. So you use moduli independence and you disentangle wall crossing, etc. From here, you don't have anything like that in EDS, right? Because they have moduli dependent.
Yeah, exactly. So if there is a parallel story, the details might be different, or maybe there's no parallel story. I'm not sure. But it's for sure is an interesting question to ask.
Are we done? Okay, I think so, right? So Francesco, thank you very much for the talk.
Thank you.